Welcome back, everybody. Last time we got introduced to the strategy of partial fractions, and today we're going to play around with that a little bit more. Recall that partial fractions was this way for us to take a rational function, something like this, where we have a polynomial in the numerator and denominator, and as long as the degree of our numerator was less than the degree of our denominator, partial fraction says, well, we can take this and break it up as a number of simpler pieces with some unknowns in there. And then we'd have to do some work to find them. But in terms of integration, the hope is that the simpler pieces we can work with and we can integrate. What we're going to do today is look at a couple of examples that highlight a couple of different aspects about this strategy. And the first one deals with this question of, well, hey, what if we don't have this degree property holding, right? What if the degree of our numerator is the same as or bigger than the degree of our denominator? Well, what can we do then? Well, it turns out we can get things into the form we want with a little division. And so here we're going to look at an example and remind ourselves how this goes. Okay, so here we were looking to compute an integral, and indeed, looking at the degrees, the degree up top is greater than or equal to the degree in the bottom. We got 3 upstairs and 2 downstairs, and so we can't just try and use partial fractions at this point. We need to do some work. We need to do some polynomial division. Well, what's nice is that if you haven't done this for a while, the idea is exactly the same as this long division of numbers. And so what I'd like to do is just talk about that for a minute and then jump over and see how it looks with our polynomial situation. All right, so just with normal numbers, the idea is, well, if we had some fraction, 7 over 3, well then we can take that fraction and there's a way to write it as just some whole number plus a fraction. In this case, we'd have some remainder over 3, right? Where that remainder is going to be either 0, 1, or 2. And the way that we do that is we'd set up this little house and we put the number up top. This 7 lives inside the house. And we put the denominator outside. Right? And then we ask the question, how many times does our denominator go into the 7, and in this case, right, it goes into it 2 times. And so then we take this 2 times 3, right, that gives us this 6. And we'd like to subtract that from our 7 and to see what's left. And that was, okay, what's left is 1. And now, this 1 we see is less than this 3, and so we're done, right? This is our remainder. Let me see if I can color code this a little bit. Oh, here we go. That's what I was meaning to do just a moment ago. We have that 1. All right, so this here is our remainder. And right, our 2 up here, right? That's the whole number, right, of 3, so that goes into 7, and then that remainder just gets put up top in our kind of fraction off to the side. And this is how we can break that up. All right, and what I claim is we do the exact same thing with our polynomial division. All right, so here we have a fraction, and again, what we'd like to write it as is just, in this case, just some number, as opposed to some number we have just some nice polynomial plus a fraction, right? Where this fraction is going to have some numerator, but this numerator's degree is going to be less than, in this case, 2. Okay, so to set this up, right, just like before, we're going to take our polynomial up top, x cubed minus 4x minus 10, and put that inside the house. And here, notice I've left a little bit of space here. This is a nice thing to do to kind of give a little spot for the degree 3, the degree 2, the degree 1, and the degree 0, the constant part of our polynomial. Just helps things line up nicely. Okay, but our question is the same as it was before. Now, what do we need to multiply this polynomial by to get it to match up with the first term here? This is really seeing how many times this polynomial goes into this big polynomial. And so here, if we just look at the first term, x cubed, and we look at the first term over here, well, to get x squared to be x cubed, we would need to multiply by x. All right, and so now what we're going to do is take this x and multiply it against the entire polynomial and put what we get underneath. So we'll get x times x, which is x cubed, x times x, which is x squared. The first time it was x times x squared, giving us x cubed. And then lastly, x times negative 6 gives us negative 6x. And just like before, with what we have underneath, we're going to subtract it. All right, so I like to do a subtraction with parentheses so we can remember that we're subtracting the whole thing. And what we get on working this out, x cubed minus x cubed is 0. 0 minus negative x squared is positive x squared. Negative 4x minus a negative 6x becomes a positive 6x minus 4x. So positive 2x. And then minus 10 minus 0 is minus 10. Okay, so at this point, we've done one step, but notice the degree of this polynomial we're left with is not yet below the degree of the polynomial we're dividing by. And so we're actually not out of our remainder yet. We need to do another step. And so here, again, looking at the leading term here, we ask, well, hey, what do we need to multiply the leading term of what we're dividing by to match that? And in this case, just 1, all right? And so we're going to add a plus 1 up top, and we'll go through this process once again. We'll take this one and multiply it against our whole polynomial and put what we get underneath. And so 1 times x squared, 1 times minus x, 1 times negative 6, negative 6. And when we subtract that polynomial from what's above, we get 0, 2x minus a negative x. That gives us 2x plus x, so 3x. And then negative 10, it'll be plus 6, negative 4. And at this point, what we're staring at, this is our remainder. And the reason why is because its degree is now less than 2, right? The degree of this is 1. Okay, and so now, just like before, we can now see how to write our original fraction, right? And the process is exactly what we saw over here, which with our numbers, right? It's going to be what we saw up top, right up here, plus our remainder divided by what we were dividing by. And so writing all that, here's our original fraction, here's our quotient, the x plus 1, and then plus our remainder divided by what we were dividing by. And now, right, in terms of what we're really up to integrating, we've broken apart our original fraction. X plus 1, we can definitely integrate that. But this part on the right, not so much yet. But, right, now we can actually use partial fractions on this piece because the degree of the numerator is small enough. So at this point, why don't you pause the video, see if you can use partial fractions on our friend over here. Write the terms that get associated and see if you can find the unknowns and integrate everything afterwards. Let's take a few minutes and work on that. All right, well, let's start talking through it. First step, right, if we want to use partial fractions, is to factor the denominator, right, because that's going to show us what we need to associate terms to. All right, and so in this case, x squared minus x minus 6 is a quadratic. So in this case, we could try to factor it just by finding the two numbers that multiply to be -6 and add to be -1. And there are numbers that work. So -3 and +2 fit the bill. And so here we are able to factor our denominator nicely. And my partial fraction says now we're going to have a term associated to both of these factors on the left. All right, so these are both linear, and so up top we'll just need to allow for some constants. All right, now we want to go ahead and find those unknowns. And to start us off, we'll just clear denominators by multiplying both sides by the denominator of our original function. And so here, if we take left and right and multiply by that denominator, the x minus 3, x plus 2, well, on the left, we'll just kill off our denominator. And on the right, when we distribute this through, on the left, the x minus 3's will cancel, and on the right, the x plus 2's will cancel. All right, and so here's what we're left with when the dust settles. And at this point, right, we remember that this equation is going to hold for any and every x, and so let's plug in some x's to get some equations involving our unknowns that we want to find. And here, because of these linear factors, there are a couple of nice x's that'll get us there pretty quickly. If we plug in -2 to kill off this factor, and if we plug in +3 to kill off this factor, life will be good. All right, so plugging in -2 for x wherever we see it on the left-hand side, we get -6 minus 4, and on the right, we get 0 plus b times -5, and we can then quickly solve for what b equals. And plugging in 3, similar story plays out. 9 minus 4 on the left, and then a times 5 plus 0 allows us to solve for a. All right, so we just need to plug in 1 for a, 2 for b, right, in our form up here. So 1 there, 2 there, and putting the pieces together now. All right, here's our original fraction that we were thinking about, right? Through our polynomial division, we saw that that broke up as x plus 1 plus this fraction. And we just did partial fractions on this piece here. And we found that a was 1. And so here we've subbed that in. And here plugged in 2 for b. Now, with all this work, we've gotten to a point where we can actually integrate. All right, so x becomes x squared over 2, 1 becomes x, and here both these denominators are linear, and so we could do a u sub off to the side, or these are just going to become a natural log of absolute value of our denominator, and here we'll have a constant multiple of 2 on the outside. It's a little plus c, and we are good to go. So, yeah, what to do if the degree of our numerator is the same as or bigger than our denominator. To get started, we'll do polynomial division, and then we'll be able to use partial fractions on the simpler fraction that's left from that process. All right. So one more example to talk about today. Here we're looking at integrating x plus 1 over x squared plus 1. And so if you haven't thought about this one yet, pause the video and play around with it for a little bit. It's a little bit weird, but take a few minutes and see what you can make of it. All right, let's talk about this. I say that it's a little bit weird because if we try and do partial fractions on this thing, we don't really get anywhere. For example, this denominator, x squared plus 1, is irreducible, right? This, if you want to think graphically, right, this parabola does not cross the x-axis, so this thing's not going to factor. And so what partial fraction says is that, well, we can take this, this fraction with an irreducible quadratic denominator, and well, we can write it as something with that denominator with possibly a linear polynomial up top. And I'll give you 2 guesses what the a and the b would end up being if we went through, the process of clearing denominators and solving for them, right? It's exactly what we have to start with. And so this sort of breaking up that partial fractions does is actually not going to be helpful here. This is already somehow broken up. Well, while I'm thinking about that, some other things we could possibly explore, maybe a u sub, right, with u being our denominator. But if we did that, the derivative would be 2x, and we kind of have that up top, but this 1, the plus 1, that's going to end up being a deal killer. That's going to mess us up. And so u sub, not so much. If we imagine that, instead that this x wasn't round, if we just had the 1 over x squared plus 1, well, then we'd be staring at the derivative of inverse tangent, and so things would be good, right? But in this case, it still is there. And so the x plus is what's making us sad in this case, right? If only there was some way of only dealing with one part of the numerator at a time. And hold the phone there is, right, we can actually break it apart some more. Right, if we break this fraction apart with this common denominator, you can write it as two fractions, one with the x on top and one with the 1 on top. And then with what we've been talking about, we'll be able to handle both of these pieces. On the left, we can do a u sub if we want, or we can kind of by hand construct the antiderivative. It'd be natural log of absolute value of x squared plus 1, but then to make everything match up, we'll need the scaling factor of 1/2. And then over here on the right, 1 over x squared plus 1, that is literally the derivative of inverse tangent, and so antidifferentiating gives us inverse tangent. And so right there, those are our antiderivatives. And so it might feel a little bit odd that this example is here in partial fractions when partial fractions ended up not being helpful. But the idea here is that while partial fractions itself wasn't useful on our function, terms like this with an irreducible denominator that's quadratic, they do show up in partial fraction decompositions. And so we do want to be able to integrate things like this. And this is the idea here. We want to, if there's two terms up top, well, let's just break things apart and deal with them individually. All right, well, that's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.